Okay, this is the first of several talks on the simplex method, which is chapter 4 in the text. And today I want to talk about section 4.1, which is called the essence of the simplex method. And we'll start with a kind of a geometrical presentation of this. And then in section 4.2, we'll talk about algebraically how the simplex method works. So we'll start with an example, the example that we looked at a lot already in the previous chapter. Let me show the feasible region for this. So I will do it as follows. Yeah, this is it. So there was the Windor Glass Company problem. And in this problem, there were 3 constraints plus the 2 non-negativity constraints. So you had the constraint x1 less than or equal to 4. That's the vertical line starting at 4, 0. You had the constraint 2x2 less than or equal to 12. That's the horizontal line, x2 equals 12 and everything below it. You had the constraint 3x1 plus 2x2 less than or equal to 18. That's the line with negative slope that crosses the x1 and x2 axes. And you had the 2 non-negativity conditions, x1 greater than or equal to 0 and x2 greater than or equal to 0. So if you graph these inequalities, you get this region in the first quadrant, this gray region, and that is the feasible region. What are called the corner points are the intersection of 2 of the lines that define the constraints. And if you look at this carefully, you will see that there are 1, 2, 3, 4, 5, 6, 7 corner points, of which 5 are in the feasible region. So I'm going to redraw this on a paper so that I can write and talk at the same time, and you can see what I'm doing. But this just to show you a very clear picture of the feasible region. And how do I end the screen share? That is the question. Stop share. Okay, excellent. So here are the 5 constraints for the feasible region. Let me just draw the feasible region again carefully. So 1, 2, 3, 4, 5. So this is the line x1 equals 4. This is the x1 axis. This is the x2 axis. 2x2 equal 12. 1, 2, 3, 4, 5, 6. That's the same as x2 equals 6. So the line 3x1 plus 2x2 equals 18. When x1 is 0, x2 is 9. When x2 is 0, x1 is 6. So this is this line. X1 greater than or equal to 0, that just means you're in the right half plane. X2 greater than or equal to 0 means you're in the upper half plane. So this is the feasible region. And what are called the corner point solutions, or the corner points, are the intersections of two lines or two edges in this picture. So, for example, if you take x1 equals 0 and x2 equals 0, the corner point is right here, 0, 0. If you take the line x2 equals 0 and x1 equals 4, the corner point is right here, x4, 0. If you take this line and this line, the intersection is this point, 6, 0. If you take this line and this line, the intersection point is there. That's the corner point. If you take this line and this line, the intersection point is there, 0, 9. If you take these two lines, the intersection point is here, 2, 6. And if you take this line and this line, the intersection point is here, which is 4, 3. So these are the corner points. There are 1, 2, 3, 4, 5, 6, 7 of them. But you'll notice that this point and this point are outside the feasible region. So the corner points feasible, CPF, is the notation that the book uses. These are the corner points in the feasible region. And they're 1, 2, 3, 4, 5. There are 5 of them. Now, in the simplex method, you're trying to find the point in the feasible region where the objective function takes its maximum value. So our objective function for this problem is z equals 3x1 plus 5x2. And the feasible regions, this whole region in the plane, there are infinitely many points in it. You can't check infinitely many points. You only have a finite amount of time. So the first statement of the simplex method is that the optimal solution, this is sometimes called the optimality test, is the largest value of the objective function, z, always occurs at a corner point feasible. So you don't have to check all the infinitely many points in this region. You just need to check the corner point feasibles. Moreover, if you want to find an optimal solution, you don't have to try every one of these points. There's a method to pick in a fairly short time the optimal solution. And it's based on the following fact of the simplex method. So let me just define what are adjacent solutions. So two corner points are adjacent if they lie on the same line, or CPF. I'm only interested in the feasible corner points. Two feasible corner points, two CPFs are adjacent if they lie on the same edge. So for example, 0, 0, and 4, 0 are adjacent because they lie on this edge of the feasible region. 0, 0, and 0, 6 are adjacent because they lie on this line. 0, 6, and 2, 6 are adjacent. They lie on the same line. Similarly, 2, 6, and 4, 3 and 4, 3 and 4, 0. So in this feasible region, there are exactly 5 pairs of adjacent CPFs, corner point feasibles. And the second part of the optimality test says if a CPF solution to the problem, right? Every point in the feasible region is a solution to the problem. It satisfies all of our inequalities. If a corner point feasible solution is better, which means greater, gives a greater value of Z. So if a corner point feasible solution is better than its adjacent corner point feasible solutions, then stop all your work. It is the optimal solution. So let me show you by looking at this example of the Zindor Glass Company, what this means. So here is our linear programming problem. We have, this is the feasible region with these 5 constraints, 3 inequalities plus the non-negativity conditions. And this is the objective function. And start by choosing any corner point feasible solution. And in fact, almost always our initial choice, the initialization, is, because it's the easiest point to find, is 0, 0. So in almost every linear programming problem, which is in sort of what we'll call a standard form, 0, 0 certainly satisfies all the constraints. Okay. And so you take the point 0, 0 and So remember, z, the objective function, is 3x1 plus 5x2, and z evaluated at 0, 0 is 3 times 0 plus 5 times 0 is 0. So the value of the objective function here is z equals 0. Then you look at the two adjacent points. So what are the points adjacent to 0, 0? The corner point feasible solutions? 4, 0 and 0, 6. Now, we're only going to check one of them. Which one do we check? This is the objective function. If you increase x by 1, z goes up by 3. If you increase x2 by 1, z goes up by 5. So you choose the direction, because there are two adjacent points. You can increase x1 or you can increase x2. You get the maximum increase by increasing x2. So increase x2, that is, you go up this line, and the first corner point feasible solution you find is 0, 6. So this is the second step. 0, 6. What is the value of z at 0, 6? The value of z at 0, 6 is 3 times 0 plus 5 times 6 is 30. So at this point, z is equal to 30. Now, at this point, you want to look at the two adjacent solutions, CPFs, 0, 0, where you started from, and 2, 6. This is z equal 30 is bigger than 0. If you move from 0, 6 to 2, 6, what happens? So let's choose next the point 2, 6. Z at 2, 6 is 3 times 2 plus 5 times 6 is 36. Okay, it's bigger. So here you are at this point, 2, 6. What are the two adjacent points? Well, these two are adjacent and these two are adjacent. The only other adjacent point you could look at is 4, 3. So choose 4, 3. Z at 4, 3 is 3 times 4 plus 5 times 3. 12 plus 15 is 27. So what do we see? At the point 2, 6, that's a CPF, a corner point feasible solution. There are two adjacent corner points. Here, and at 2, 6, z, the objective function has the value 36. At the two adjacent points, here z is smaller, it's 30. Here z is smaller, it's 27. So at this point, the value of z is bigger than at the two adjacent points. So at that point, we stop. And the optimal value of z is 36. We don't have to look at the other points that might be corner point feasible solutions. The optimality test in the simplex method says that if you have a corner point feasible solution, a corner point where the objective function is larger than it is at any of the adjacent points, then this is the largest the objective function can be anywhere. You don't have to look anywhere else in the region. So in doing the simplex method geometrically, we have our feasible region, we have the corner points, you have the corner points that lie in the feasible region, not all do, these two don't, for example. You have the corner points that lie in the feasible region. Start by choosing 0, 0, because you know that's always a corner point in the feasible region. Look at the adjacent points, move in the direction that increases z the most. At that point, look at the adjacent points. Always move in a direction that will increase z. Or if you have no choice, this is where you move to. And once you get a corner point feasible solution whose value, for which the value of the objective function is bigger than it is at the two adjacent points, you know this is the biggest it can possibly be. Biggest it can possibly be. That's the simplex method. Now, I'm using the simplex method here in a simple case. They're just two variables, x1 and x2, and they're just 5 inequalities. In real problems, you might have 1,000 variables and 10,000 inequalities, and it can only be solved by a large computer, but the idea was going to be the same. Now, let me just show you the first step. This is in section 4.2 of setting up the simplex method algebraically, because it's always easier to solve two linear equations than two linear inequalities. And what we do is we want to convert every inequality to an equality. So for example, we have the constraint x1 less than or equal to 4. So we introduce a new variable, what is called a slack variable, x3, and we replace x1 less than or equal to 4 by x1 plus x3 equals 4. And if x3 is greater than or equal to 0, then x1 plus x3 equals 4. A solution of this is the same as a solution of x1 less than or equal to 4, right? Because if this is positive, x1 is smaller than 4. So I've converted this inequality to an equation. We had 2x2 less than or equal to 12. We introduce a slack variable x4 and write this as, and I want every variable that we introduce, for every inequality, when we introduce a slack variable, it's a new variable. So this will be x4. So we have 2x2 plus x4 equals 12. And x4 has to be non-negative. And for the inequality 3x1 plus 2x2 less than or equal to 18, we introduce a slack variable x5. So we have 3x1 plus 2x2 plus x5 equals 18, and x5 is greater than or equal to 0. So I started off with these 3 inequalities. I introduced 3 slack variables, x3, x4, x5, and now I get equations. And all of my inequality, all of my variables, x1 and x2, those were non-negative to begin with. x3, x4, x5 are non-negative. I get a set of equations, and solutions of these equations satisfying these conditions are exactly the same as solutions of my inequalities. So we'll talk about this more in the next lecture, but this is the first step in dealing with the simplex method algebraically. You convert inequalities to equalities by introducing new variables that are called slack variables. So for the first homework assignment in chapter 4, actually for the first 2 homework assignments, what I've done in this talk is everything you need to know to solve the problems. And I'll solve some of the problems in the next lecture.